Now in this session, I look at a block diagram example. In a previous session, I looked at the transfer function of a system having all the components. Now here, if you see, we talked about the process, the valve, the current to pressure transducer, the controller, and the measurement device. And just to recall that we derived the transfer function between this output and the set point, which is given as all the transfer function between the two variables, meaning all the transfer function between the output and set point, which were GP, GV, GIP, GC, and GM in the numerator, and in the denominator 1 plus all the transfer function within the loop. So within the loop, the transfer functions were GP, GV, GIP, GC, and GM. So this is the relation between the output and the set point. Why are you considering all these different elements? And if you look at the other transfer function I looked at, it was presented in a simplistic way with the process and the controller. And again, the transfer function between the set point and the output was ys over y set point was given by the transfer function between y and y set point, GPGC in the numerator, and the denominator we had 1 plus all the transfer functions within the loop. Now, this simplified form of the transfer function is used to design the controller, meaning that when we have a process with all the elements, we find a simplified model to design the controller, because most controller tuning algorithms are based on either first order or second order process. However, when we try to implement the controller, we need to consider all the elements, because these are the really existing elements and the control performance dependent on all of these different elements. So we need to consider all the elements when we're trying to analyze the performance of a controller, analyze the stability, and so on. Okay, so that's the purpose of having all of these different elements in the control loop when we are trying to analyze the stability and other performance criteria of a closed loop system. Let's look at what are the different elements for this particular example. Now this is the what is called the so-called blending process, where a concentrated liquid is coming in, where its composition is X1 and flow rate is W1, and the objective is to maintain a certain composition of the outlet liquid. Now this blending process, as I mentioned when we're discussing the examples, typically in plants, concentrated liquids are imported and then mixed with a pure liquid to get a final product that's usable for this particular plant. Now, for example, this can be a sulfuric acid. So sulfuric acid may be imported as suppose 90 or 95% and then mixed with water to produce sulfuric acid, which is an acid of desired concentration, maybe 5%, 10%, or so on. So the output is the mass fraction of the main component. Here, just simply for the sake of simplification, I took A. And the input is the mass flow of the stream 2, meaning that how much of the pure diluent you are using. And the disturbance for this case can be the mass fraction of the concentrated stream. So this can be imported from different sources. This can be imported at different time with different concentrations. So this composition is not constant. So that acts as a disturbance for the process. Now, as you understand, this outlet X, that is the mass fraction of the component in the final stream, will depend on both the flow rate of the diluent and also will depend on the concentration of that A in the feed stream. We can find out a model between these variables. Okay, now before going to that, let's look at the elements within this system. So we have the process, which is represented by this mixing system, And then we have the composition sensor and transmitter. So we have to measure the composition, which is represented by this analyzer and transmitter. We have the controller represented by this in the diagram, and we have the I to P, or the current to pressure converter, and we have the final control element. Now we need to look at what are the dynamics of each of these different elements. Now starting with the process, from our experience with first principle modeling and with system identification, we see that the transfer function between the output, meaning the composition of A in the outlet stream, and that of the input, meaning the flow rate of the diluent, can be expressed by a simple first order transfer function. So in the divisional form, x prime s and w2 prime s is represented by this first order model. In the same way, the transformation between the in output and the disturbance, meaning the x1, that's the composition of the inlet stream, can be represented by another first order transfer function. Okay, now we see that this xs, or the output, which is the composition of the outlet stream, is affected by these two variables x1s and w2s. Okay, now when they are affected by two variables, the overall relation can be represented by simply this formulation of an equation. Now in the block diagram representation, this can be represented by this process. So we have seen the x1, which is the disturbance coming in, going through the corresponding transfer function, and then w2, which is the input going through another transfer function, and when the two effects are added together, that gives the output variable, which is xs for this case. Okay. Now this is the representation of the process. Now let's look at the other components. Now typically the current to pressure transducer, what it does is that the controller output is in the form of a current signal, and the valves are typically pneumatic valve, meaning they operate under pressure signal. So we have to convert this electrical or current signal into a pressure signal to operate the valve. Typically, that's nothing but simply a gain, meaning that a conversion factor between the current and pressure. So that can be represented by simply this one block, where the controller output in terms of the current signal is converted into that in terms of a pressure signal. Okay. So now let's look at the valve part. For the valve, there may be some dynamics because valve has their own inertia. So to convert the valve opening into flow rate, we need a transfer function with a lag dynamics, meaning that there may be some inertia in the valve, which can be represented by a first order dynamics, typically having a very small time constant. Okay? So this relation between the output itself and the input signal to the valve can be represented by a first order dynamics. Now the sensor, it can have also its own dynamics. Say the measured value and the real value, the relation can be represented by a first order transfer function. In many cases, this will be simply a gain, meaning that the measured value and the real value can be related by a conversion factor. In any case, the relation can be represented by either as a first order transfer function or as a gain only. So note that the real variable is in terms of the mass fraction. However, the value that goes to the controller in terms of a current signal. It can be a voltage signal as well. So for this case, we're considering current signal. So there will be a conversion between these two. Now, if we look at the controller then, The controller may have different forms. It can be a proportional only controller. It can be a PI controller, PID controller. So if it's a PI controller, its dynamics can be represented by this transfer function. And in the block diagram form, we'll have this relation. Now, this error signal will be coming as a current signal. Also, the controller output is typically a current signal. Okay, but there will be transfer function between this error signal and the controller output signal or the input signal to the process. Okay, now the set point also needs to be expressed in a proper way, meaning that we can, for example, for this case, the set point value will be specified in terms of mass fraction. However, for the controller, it needs a current signal. Okay, so we need a conversion between this mass fraction and the current signal, and that can be expressed by this block diagram. Now, if we plug in all of these elements together, we end up getting this. Here again, this part represents the process relation, which is the X is the summation of the influence by W2 and X1. And this W2 is determined by the valve, where the valve gets the output signal from the controller, from the current to pressure transducer, and then produces the input signal to the process. Again, the current to pressure transducer is represented by this element, where a current signal comes in from the controller and a pressure signal that comes out of the transducer and then goes to the valve. Now, this controller is represented by this, for this PI controller, represented by this transfer function, where the error signal comes in and it produces a current signal that goes to the current to pressure transducer. And then the set point, which is expressed in terms of mass fraction, it's converted into a current signal that goes to the controller. Now, output at the same way, the output is also goes through this element, because the output we express in a mass fraction, but that's converted into a current signal that goes to the controller, and then the difference between the set point and the output produces the error signal for the controller. Now, as I said, this expanded diagram is used for analyzing the stability and other performance of the controller. However, for the purpose of controller design, we may need to further simplify this. So typically, we can have all of these elements, that GIP, GV, and GP can be considered within the process. So if we do that, we end up getting a simplified diagram for this case, where this GP, the process transfer function, is expressed as a combination of all these three. So we're left with the controller, the disturbance, and the measurement device. Okay. So if we have in the simplified form, we'll have this to be represented by the process, the controller, the measurement device, which can be simply a gain, and the same measurement device here, and the transfer function between the output and the disturbance. Now, if we look at this model for the entire process, again, the transfer function we can represent as, if you write x over x set point, it will be all the elements between these two variables. That's on the numerator. It will be GP, GC, GM, and in the denominator 1 plus all the elements within the loop. So remember, the loop is between this and this point. So it will be 1 plus GP, GC, and GM. Okay. So in summary, we'll have a simplified representation of the process to design the controller. However, to analyze the performance of the controller, we need to consider all the elements in details.